In this video, we will get a better interpretation of the definite integral. We will do this by looking at its units. Recall, if we know a function's derivative, that is, we know that f of t is the derivative of capital F of t, then we can find the change in f of t from t equals a to t equals b as the integral from a to b of little f of t dt. We can visualize this as the area under the graph of little f of t from t equals a to t equals b, or algebraically as the limit as n goes to infinity of the sum from I equals 1 to n of f of ti times delta t. Since this can be such a difficult computation, we have used our calculators to compute this. Let's remember also that the units of f prime of t, that is, the units of the derivative of f of t, are the units of f of t divided by the units of t. And because little f of t equals f prime of t, that means the units of little f of t are the units of capital F of t divided by the units of t. Using all this information, can we figure out what are the units of the integral from a to b of f of t dt? We can start by using the fact that the integral from a to b of f of t dt can be written as this sum. So the units of the integral are the same as the units of the sum. But if we add a group of numbers up, the units of that sum are the units of each thing we're adding up. So the units of this sum are the units of f of t times the units of t. But now, using that little f of t is the derivative of capital F of t, we know the units of f of t equal the units of capital F divided by the units of t. So we can rewrite this as the units of capital F of t divided by the units of t times the units of t. But this can be simplified as just the units of f of t. So we have found that the units of the integral from a to b of f of t dt are the units of capital F of t. Let's now look at how we can come to this conclusion from another point of view. The change in f of t from t equals a to t equals b can be very simply calculated, as we did when we were computing derivatives, as f of b minus f of a. But we know from what we learned earlier that the change in f of t from t equals a to t equals b is the integral from a to b of f of t dt. So since all of these things are equal, the units of the integral are simply the units of f of b minus f of a, but those are the units of f. So we again see here that the units of our integral from a to b of little f of t dt equal the units of capital F. But what we found here is something more important. We found that for f of t equal to the derivative of capital F of t, the integral from a to b of f of t dt equals f of b minus f of a. Or in other words, substituting that f of t is the derivative of capital F, we have that the integral from a to b of capital F prime of t dt equals f of b minus f of a. This very important result is called the fundamental theorem of calculus. Let's now use the fundamental theorem to look at an example. Suppose that you begin your retirement savings with a $2,000 deposit. After your initial deposit, you continue to make weekly contributions totaling $5,000 per year and accrue interest until you retire. Suppose that the amount of money in your retirement account, R of t, grows at a rate of R prime of t equals 5100 times e to the 0.05 t, where t is the number of years that your retirement account has been open. How much does your retirement account grow in the 10th year? To answer this, we want to change our question to be in terms of our functions. The term, how much does your retirement grow, is asking what is the change of R of t. And in the 10th year means from t equals 9 to t equals 10. So what we want to find is what is the change of r of t from t equals 9 to t equals 10. In other words, what is r of 10 minus r of 9? It's important to point out that our question is about the function r of t, but the only information we have is about its derivative r prime of t. So to take the information about r prime of t and bring it back to information about r, we need to use the fundamental theorem, which says that r of 10 minus r of 9 is the integral from 9 to 10 of r prime of t dt. And using that r prime of t is 5100 e to the 0.05 t, this becomes the integral from 9 to 10 of 5100 e to the 0.05 t dt, which we can compute with a calculator to be $8,201.73. So we can conclude that the retirement account grows by $8,201.73 in the 10th year. It's worth pointing out that $5,000 of that is coming from our investments, and the other $3,200 is coming from interest on our previous contributions. Let's now come back to our example, but ask the question, how much money do you have in your retirement account after 30 years? Again, to answer this, we want to change our question to be in terms of our functions. The question, how much money do you have in your retirement account, is asking what is r of t, and the term after 30 years says when t equals 30. So what we are trying to answer is what is r of t when t equals 30. In other words, what is r of 30? Notice the difference between this question and the question we asked in the last part. In the last part, we wanted to know how much r changed, but here we want to know what r is. But by knowing the rate of change, the fundamental theorem only allows us to figure out how much a function changes. To answer this, we need to find the change in r of t from t equals 0 to t equals 30. Because we can write the change in r of t from t equals 0 to t equals 30 as r of 30 minus r of 0, which could be computed using the fundamental theorem as the integral from 0 to 30 of 5100 e to the 0.05 t dt, which comes to roughly 355,132. But we want to know what is r of 30. Solving this equation for r of 30, we get that r of 30 is roughly 355,132 plus r of 0. But what's r of 0? Here, we use the fact that we begin our retirement savings with a $2,000 deposit. So r of 0 is 2,000. Which means that r of 30 is 355,132 plus 2,000, which is 357,132. So we can conclude that after 30 years, you will have $357,132 in your retirement account.